Hello everyone. Today we'll study basis and dimension. First of all, let me introduce finite dimensional vector space. Let V be a vector space. If there exists a finite subset S which spans V, then we say V is finite dimensional. Otherwise, we say V is infinite dimensional. So, if there's a finite subset S which spans V, then V is finite dimensional. If there's no finite subset S that spans V, then we say V is infinite dimensional. Next, let me introduce basis. Let V be a finite dimensional vector space, and let S equal to V1, V2, Vn. Let S be a subset of V. We say S is a basis of V if S is linearly independent, and S spans V. So, if S is linearly independent and S spans V, then we say S is a basis of V. So if S is linearly independent and S spans V, we say S is a basis of V. Next, let me show you a special case. If V is the zero vector space, which means V contains only one vector, the zero vector. If V is the zero vector space, then the basis of V is the NP set. If V is the zero vector space, then the basis of V is the NP set. Because we define NP set to be a linearly independent set, and we define span of NP set to be the set of zero vector. Therefore, the NP set is linearly independent, and the NP set spans V. We say NP set is a basis of the zero space, of the zero vector space. That's a special case. Next, let's look at a theorem. Every finite dimensional vector space has a basis. How can we prove it? First of all, let V be a finite dimensional vector space. Then, by definition of finite dimension, it means there exists a finite subset S in V such that S spans V. There exists a finite subset S which contains V1, V2, Vn in V. Such that S spans V. Now, if S is linearly independent, there are two cases. S is either linearly independent or linearly dependent. Is S is linearly independent, then we are done. Since S spans V and S is linearly independent, then S is a basis of V, we are done. However, what if S is linearly dependent? What if S is linearly dependent? Then, one of the vectors in S can be noted as a linear combination of the other vectors. Then, one of the vectors in S can be noted as a linear combination of other vectors. Say, let's call this vector E1. Then Then there is a vector U1 in S. U1 is one of these vectors, such that U1 can be written as a linear combination of all other vectors in S. U1 can be written as a linear combination of other vectors in S. Next, I let S1 equal to S take away U1. Then, by the plus minus theorem, if U can be written as a linear combination of other vectors in S, then if I remove U from S, the span of the set is the same as span of S. By plus minus theorem, span of S is the same as span of S take away U1. Which means span of S equal to span of S1. Now check S1. If S1 is linearly independent, then S1 is the basis of V. There are two cases. S1 could be either linearly independent or linearly dependent. If S1 is linearly independent, then S1, since S1 equals to span of S, then S1 spans V. Since S1 is linearly independent and it spans V, S1 is the basis of V. Otherwise, if S1 is linearly dependent, second case, if S1 is linearly dependent, then there exists a vector U2 in S. There is a vector U2 in S1, such that U2 can be written as a linear combination of other vectors in S1. So repeat the same process. Let S2 equal to S1 take away U2. Then again by plus minus theorem, span of S1 equal to span of S1 take VU2. Hence, span of S equal to span of S1, and span of S1 equal to span of S2. S2 is S1 take VU2. Now again, if S2 is linearly independent, then S2 is the basis of V. Because span of S2 equal to span of S, that means S2 spans V. If S2 is linearly independent, it's the basis of V. If S2 is linearly dependent, then repeat the same process. Then, after repeating the same process finitely many times, we can repeat this process at most n times. We can repeat this process at most n times. Because in S, there are n vectors in S. We can remove vector from S at most n times. After repeating the same process finitely many times, we can eventually obtain a linearly independent set Si. We can eventually obtain a linearly independent set Si. Such that span of S equal to span of S1 equal to span of S2 equal to span of Si. And we know that span of S is V. Span of S is V, since S spans V. Since Si is a linearly independent set, and Si spans V, then Si is a basis of V. Hence Si is a basis of V. And in the worst case, if we repeat the same process exactly n times, that means all vectors in S will be removed. If all vectors in S are removed, what's left is NP set. Since V equal to the span of NP set, V must be the zero vector space. And we know that if V is in the zero vector space, then the basis of V is NP set. So every finite dimensional vector space has a basis. Let's complete the proof. Every finite dimensional vector space has a basis. Next, let's create an example. Let S be the set of two vectors, 2, 3, and 5, 1. Show that S is a basis in R2. In order to show S is a basis in R2, we must show that S is linearly independent and S spans R2. Let's first of all try to show that S is linearly independent. Let me call these two vectors v1, v2. I first of all set k1, v1 plus k2, v2 equal to 0, equal to the 0 vector. If an only solution to this vector equation is k1 equal to 0 and k2 equal to 0, then S is linearly independent. Next, let's try to show that S spans R2. In order to show S spans R2, I first of all pick arbitrary vector in R2. Let B equal to B1, comma B2. Let B be an arbitrary vector in R2. Then set K1 V1 plus K2 V2 equal to B. If this vector equation is consistent, which means if there's solution for K1 and K2, then S spans R2. So let's solve these vector equations. First of all, we can rewrite this vector equation using augmented matrix. The augmented matrices of the above vector equations are these two matrices. For the first equation, I can put a component of V1 in the first column, put a component of V2 in the second column, and then put a component of 0 vector in the third column. We know that 0 vector in R2 is 0, 0. And for the second vector equation, for its augmented matrix, I put a component of V1 in the first column, component of V2 in the second column, and a component of B in the third column. I get B1, B2. Then we can solve both equations, use Gauss-Jordan elimination. However, if we observe these matrices, we can see that the matrix in front of constant is a square matrix. So I can rewrite this augmented matrix using matrix equation. Equivalently, the above augmented matrix can be written as AS equal to 0 and AS equal to B. Where A is the matrix 2, 5, 3, 1, 2, 5, 3, 1. X is the variables. X is the unknowns K1, K2. X is the unknowns K1, K2. 0 is the 0 vector, 0, 0. That's a constant. B is the vector, it's a column vector B1, B2. B is a column vector B1, B2. Next, we take determinant for matrix A. If determinant of A is not 0, then by equivalent statements, the homogeneous system AS equal to 0 has only the trivial solutions. That means the only solution to K1, K2 is K1 equal to 0 and K2 equal to 0. If in this vector equation, the only solution is K1 equal to 0, K2 equal to 0, that means vectors V1 and V2, they are linearly independent. So S is a linearly independent set. Also, if determinant of A is not 0, then the system AS equal to B by equivalent statement is always consistent for all column vector B. AS equal to B is always consistent for all column vector B, which means this vector equation is always consistent for all B. If this vector equation is always consistent for all B, then S spans R2. Since S is linearly independent and S spans R2, then S is a basis in R2. Therefore, if determinant of A is not 0, S is a basis in R2. However, if determinant of A is 0, then by equivalent statements, the homogeneous system AS equals 0 has non-trivial solution, which means there exist non-zero solutions for K1 and K2. If in its vector equations there exist non-zero solutions for K1 and K2, that means vectors V1 and V2, they are linearly dependent. Therefore, S is linearly dependent. Also, if determinant of A is 0, then by equivalent statements, the system AS equal to B is not always consistent for all column vector B. Since this equation is not always consistent, since this vector equation is not always consistent for all B, then S doesn't span R2. Since S is linearly dependent and S doesn't span R2, then S is not a basis in R2. Therefore, if determinant of A is 0, S is not a basis in R2. So, the determinant for matrix A. If determinant of A is not 0, then S is a basis in R2. If determinant of A is 0, then S is not a basis in R2. So here, take determinant for matrix A. For a 2 by 2 matrix, the determinant is 2 minus 15, which is negative 13. Since it's not 0, then S is linearly independent. And S spans R2. Hence, S is a basis in R2. Next example, let S be the set of two vectors, 1, 4 and 2, 1. Show that S is a basis in R2. In order to show S is a basis in R2, we must show that S is linearly independent and S spans R2. Let's first of all show that S is linearly independent. So let me call these two vectors V1, V2. First of all, set K1, V1 plus K2, V2 equal to the 0 vectors in R2. If an only solution to this vector equation is K1 equals 0 and K2 equals 0, that means S is linearly independent. Next, let's try to show that S spans R2. So first of all, I pick arbitrary vector in R2. Let B equal to B1, B2. Let B be an arbitrary vector in R2. Then set K1, V1 plus K2, V2 equal to B. If this vector equation is consistent, then S spans R2. So, for these vector equations, I can rewrite both equations using augmented matrix first. The augmented matrices of the above vector equations they look like this. For the first equation, put component of V1 in the first column, put component of V2 in the second column, then put component of the 0 vector in the third column. The 0 vector in R2 is 0, 0. And for the other vector equation, its augmented matrices are V1 in the first column, component of V2 in the second column, and component of B in the third column. Component of B is B1, B2. Then we can solve these equations using Gauss-Jordan elimination. However, if the matrix in front of constant is a square matrix, then there's a shortcut. Equivalently, the above augmented matrices can be written as a matrix equation. AS equal to 0 and AS equal to B. Where A is the matrix 1, 2, 4, 1. X is the unknowns K1, K2. Zero is a zero vector 0, 0. B is a column vector B1, B2. Then the determinant for matrix A. If determinant of A is not 0, then S is linearly independent and S spans R2. If determinant of A is 0, then S is linearly dependent and S doesn't span R2. Here, the determinant for matrix A. Determinant of A here is 1 minus A, which is -7, which is not 0. So, by equivalent statements, S is linearly independent. And S spans R2. Hence, S is a basis in R2. By equivalent statements, if determinant of A is not 0, S is linearly independent and S spans R2. However, if determinant of A is 0, then S is linearly dependent and S doesn't span R2. Next example, let S be the set of two functions, S squared plus 1 and 2S plus 3. Determine whether S is a basis in P2. In order to determine whether S is a basis in P2, we must determine whether S is linearly independent and whether S spans P2. Let's first of all try to determine whether S is linearly independent. Let me call these two functions f and g first. I first of all set k1 times f of x plus k2 times g of x equal to 0. If the only solution to this vector equation is k1 equals 0 and k2 equals 0, that means functions f and g, they are linearly independent. So S is a linearly independent set. Next, we try to determine whether S spans P2. So I first of all pick arbitrary vector in P2. P2 is a set of all polynomials with degree less or equal to 2. So we must pick arbitrary second degree polynomial, which is C0 plus C1x plus C2s squared. That's an arbitrary second degree polynomial. Let P of x be an arbitrary polynomial in P2. Then we set k1 times f of x plus k2 times g of x equal to P of x. If this vector equation is consistent for all P of x, then we say S spans P2. Otherwise, S doesn't span P2. Next, we can rewrite both vector equations using augmented matrices. the above augmented matrices, the above vector equations can be expressed by the following augmented matrices. For the first vector equation, for its augmented matrix, we can put a coefficient of function f and g in columns. Now, make sure write all coefficients in the same order. Then we write coefficient for 1 first, for a constant first. Then write coefficient for x next row. Write coefficient of x squared in the next row. In function f, coefficient of constant is 1. Coefficient of x is 0. Coefficient of x squared is 1. In function g, coefficient of constant is 3. Coefficient of x is 2. Coefficient of x squared is 0. And then 0 means coefficient of constant is 0. Coefficient of x is 0. Coefficient of x squared is 0. For the second vector equation, I first put the coefficient of function f in the first column, which is 101. Then put the coefficient of g in the second column, which is 320. Then put the coefficient of p in the third column. Coefficient of p is the coefficient of constant is C0. Coefficient of x is C1. Coefficient of x squared is C2. Next, let's solve both systems. Here, since the matrix in front of the constant is not a square matrix, we cannot take determinant for a non-square matrix, so there's no shortcut. The only choice for us is Gauss-Jordan emulation. So solve both systems using Gauss-Jordan emulation. Now, let's observe these two systems. We can see that the entries in front of the constant looks exactly the same. So instead of solving two matrices individually, we can combine both of them together as one matrix. So the first column is 1, 0, 1. Second column is 3, 2, 0. Put the 0 vector here. 0, 0, 0. That's the 0 vector. Then put C1, C2, C3. Put C0, C1, C2 in the last column. That's P of x. Then solve an equation for K1, K2 in both systems. So let's reduce the matrices. That's a leading one already. We try to make all entries below leading one to be 0. I can multiply first row by -1, add it to the third row. I get 1, 3, 0, C0, 0, 2, 0, C1, 0, -3, 0, C2 minus C0. Multiply first row by -1, add it to the third row. Next, in the second row, try to make leading one here. Here I can divide second row by 2. Divide second row by 2. I have 1, 3, 0, C0. 0, 1, 0, half of C1. 0, -3, 0, C2 minus C0. Next, that's a leading one. I try to make all the entries above and below leading one to be 0. So I can multiply second row by -3 added to the first row. I get 1, 0, 0. Multiply second row by -3 added to the first row. I get C0 minus 3/2 C1. I try to make 0 here, so I can multiply second row by 3 added to the third row. Leave second row the same. I get 0, 0, 0. That's C0 minus C2 minus C0 plus 3/2 C1. Next, I can write this back to two matrices, to two systems. I can rewrite this back to two systems. For the first system, look at the first three columns. For the first system, look at the first three columns. I get 1, 0, 0, 0, 1, 0. The third column is 0, 0, 0. And for the other matrix, look at the first column, second column, and the fourth column. I have 1, 0, C0 minus 3/2 C1, 0, 1, half of C1, 0, 0, C2 minus C0 plus 3/2 C1. That's how I separate this into two matrices. Write it back into two matrices. Then, in the first equation, you can see that the only solution, is K1 equal to 0, K2 equal to 0. If the only solution is K1 equal to 0, K2 equal to 0, that means S is linearly independent. If the only solution is K1 equal to 0, K2 equal to 0, that means S is linearly independent. Look at the second equation. Look at the second system here. In the third row, C2 minus C0 plus 3/2 C1. This is not always 0. If we get 0 equal to some non-zero number here, if I get 0 equal to some non-zero constants, that means this system is inconsistent. The system of equation here is inconsistent. So since C2 minus C0 plus 3/2 C1 is not always 0, then the vector equation K1 times f of x plus K2 times g of x equal to p of x is not always consistent. Hence, S doesn't span P2. Since S doesn't span P2, S is not a basis of P2. Since S doesn't span P2, S is not a basis of P2. Next example, let S be a set of 5 matrices. Determine whether S is a basis of M22. In order to determine whether S is a basis of M22, we need to determine whether S is linearly independent and whether S spans M22. So let's first of all try to determine whether S is linearly independent. Let me call these matrices A, B, C, D, E. And then we set K1A plus K2B plus K3C plus K4D plus K5E equal to 0. If the only solution to this vector equation is K1 equals 0, K2 equals 0, K3 equals 0, K4 equals 0, and K5 equals 0, then the matrices A, B, C, D, E, they are linearly independent. So S is linearly independent. Otherwise, S is linearly dependent. Next, we try to determine whether S spans M22. So, in order to determine whether S spans M22, we pick arbitrary element in M22. So let M equal to, for example, make it simple, M1, M2, M3, M4. Let M be arbitrary element in M22. That's an arbitrary matrix in M22. Then we set K1A plus K2B plus K3C plus K4D plus K5E equal to M. If this vector equation is consistent for all M, then we say S spans M22. Otherwise, S doesn't span M22. Next, let me rewrite the vector equations using augmented matrices. The above vector equations can be expressed by the following augmented matrices. For the first vector equation, for its augmented matrices, I can put entries in matrix A in the first column. Put entries in matrix A in the first column. I have 2, 1, 0, 0. Next, put entries in matrix B in the second column. I get 1, 0, 3, 0. Next, put entries in matrix C in the third column. I get 0, 0, 2, 3. Next, put entries in matrix D in the next column. I get 0, 3, 0, 0. Next, put entries in matrix E in the next column. I have 2, 0, 0, negative 9. Next, put entries in 0 matrix in the next column. The entries of 0 matrix is 0, 0, 0, 0. That's an augmented matrix of the first vector equation. The augmented matrix of the second vector equation, I can do the same thing. Put entries in vector A in the first column. I get 2, 1, 0, 0. Next, put entries in matrix B in the second column. I get 1, 0, 3, 0. Next, put entries in matrix C in the next column. I get 0, 0, 2, 3. Next, put entries in matrix D in the next column. I get 2, 0, 0, 9. Sorry, I get 0, 3, 0, 0. Next, put entries in matrix E in the next column. I get 2, 0, 0, 9. 2, 0, 0, negative 9. Next, put entries in matrix M in the next column. I get M1, M2, M3, M4. Now, Since the matrix in front of a constant is not a square matrix, we cannot take determinant for a non-square matrix. So the only choice for us is using Gauss-Jordan elimination. So Gauss-Jordan elimination is the only choice for us. Since in both matrices, the entries in front of before the constant looks exactly the same. The entries before the constant, before the last column, looks exactly the same. We can combine, instead of solving two matrices, we can combine two matrices together. Make it a little easier, we can combine two matrices together. Since the entry before the constant looks exactly the same, since the entries before the constant looks exactly the same, we can combine two matrices together. So instead of solving two matrices, we can solve one matrix. Put 0 here, 0, 0, 0, 0. That's the 0 matrix. Then followed by M1, M2, M3, M4. That's matrix M. Then reduce the matrices use Gauss-Jordan elimination. Reduce the matrices using Gauss-Jordan elimination. So in the first row, try to make leading one here first. I can interchange row 1 and row 2. I can first of all interchange row 1 and row 2. So I get 1, 0, 0, 3, 0. 0, M2. Second row is 2, 1, 0, 0, 2, 0, M1. Next row is 0, 3, 2, 0, 0, 0, M3. Next row is 0, 0, 3, 0, -9, 0, M4. Next, let the leading one. We try to make all entry below leading one to be 0. So I can multiply first row by -2, add it to the second row. Multiply first row by -2, add it to the second row. First row stays the same. I get 1, 0, 0, 3, 0, 0, M2. Multiply first row by -2, add it to the second row. I get 0, 1, 0, -6, 2, 0, M1 minus 2 M2. Multiply first row by -2, add it to the second row. And the third row and the fourth row stays the same. I get 0, 3, 2, 0, 0, 0, M3. 0, 0, 3, 0, -9, 0, M4. Next, in the second row, we have a leading one here already. That's a leading one. Try to make all entries above and below leading one to be 0. Here, I can multiply second row by -3, add it to the third row. Multiply second row by -3, add it to the third row. So leaving the first row the same. I get 1, 0, 0, 3, 0, 0, M2. Second row is 0, 1, 0, -6, 2, 0, M1 minus 2 M2. Multiply second row by -3, add it to the third row, I get 0, 0, 2. -3 times -6 is 18. 18 plus 0 is 18. That's -6. 0. Multiply second row by -3, add it to the third row. I get M3 minus 3M1 plus 6M2. And then we leave the fourth row the same. I get 0, 0, 3, 0, -9, 0, and 4. Next, in the third row, try to make a leading one here. Here I can divide the third row by 2. I can divide the third row by 2. So multiply third row by half. So first row stays the same. I have 1, 0, 0, 3, 0, 0, and 2. Leave second row the same. I get 0, 1, 0, -6, 2, 0, M1 minus 2M2. Divide the third row by 2. I get 0, 0, 1, 9, -3, 0, half of M3. Minus 3/2 of M1 plus 3M2. And then leave the fourth row the same. I get 0, 0, 3, 0, -9, 0, and 4. Next, let the leading one in the third row. We have to make all entries above the leading one to be 0, above or below leading one to be 0. So I can multiply the third row by -3, add it to the fourth row. Multiply the third row by -3, add it to the fourth row. So first row stays the same. I get 1, 0, 0, 3, 0, 0, M2. Leave second row the same. 0, 1, 0, -6, 2, 0, M1 minus 2, M2. Leave the third row the same. I get 0, 0, 1, 9, -3, 0, half of M3 minus 3/2 of M1 plus 3M2. Then multiply the third row by -3, add it to the fourth row. I get 0, 0, 0, -3 times -3 times 9 is -27. -3 times -3 times -3 is +9. 9 plus -9 is 0. 0. So multiply the third row by -3, add it to the fourth row. I get M4 minus 3/2 M3 plus 9/2 M1 minus 9M2. Next, in the fourth row, we try to make the first non-zero entry to be 1, to be leading 1. So I can divide the fourth row by -27. Divide the fourth row by -27. So leave the first three rows the same. I got 1, 0, 0, 3, 0, 0, M2, 0, 1, 0, negative 6, 2, 0, M1 minus 2, M2, 0, 0, 1, 9, negative 3, 0, half of M3 minus 3 half of M1 plus 3 M2. The fourth row is 0, 0, 0, 1, 0, 0. Divide the first row by negative 27. I get negative 1 over 27 M4 plus 1 over 18 M3 minus 1 over 6 M1 plus 1 over 3 M2. Next, let the leading one in the fourth row. Try to make all entries above leading one to be 0. So what we can do here is, I multiply the third row by negative 3, multiply the fourth row by negative 3 added to the first row. I get 0, 1, 0, 0, 0, 0, 0. Multiply the fourth row by negative 3 added to the first row. I get 1 over 9 M4 minus 1 over 6 M3 plus 1 over 2 M1. That's negative M2. Negative M2 plus M2. They get cancel. In the second row, I multiply the fourth row by 6, added to the second row. Multiply fourth row by 6, added to the second row. I get 0, 1, 0, 0, 2, 0. Multiply the first row by 6, added to the second row. I get 2 over 9 M4 plus 1 over 3 M3 6 times negative 6 M1 is negative M1. Negative M1 plus M1 they can cancel. 6 times 1/3 of M2 is 2 M2. 2 M2 plus negative M2 they can cancel. Next, I can multiply the fourth row by negative 9, added to the third row. Multiply fourth row by negative 9 added to the third row. I get 0, 0, 1, 0, negative 3, 0. That's 1/3 of M4. Negative 9 times 1 over 18 is negative half of M3. Negative half of M3 plus half of M3 they get cancelled. Negative 9 times negative 1 over 6 of M1. That's 3 over 2 M1. 3 over 2 M1 cancels negative 3 over 2 M1. Negative 9 times 1/3 of M2 is negative 3 of M2. Negative 3 of M2 cancels positive 3 of M2. So what's left is 1/3 of M4. And we leave the fourth row the same. 0, 0, 0, 1, 0, 0. 1 over 27, negative 1 over 27 of M4 plus 1 over 18 of M3 minus 1 over 6 of M1 plus 1 over 3 of M2. Then next we can separate the matrices. If I separate the matrices, I get this 5 column plus 0, 0, 0. That's the first matrices. 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 0, 1, 0, negative 3, 0, 0, 0, 0, 1, 0, 0. That's the first matrices. Next, I keep the first 5 columns and the last column. That's the second matrices. That's the second matrices in the reduced echelon form. 1, 0, 0, 0, 0. 1, 9 of M4 minus 1, 6 of M3 plus 1 half of M1. Second row is 0, 1, 0, 0, 2 followed by 2, 9 of M4 plus 1 third of M3. Next row is 0, 0, 1, 0, negative 3 followed by 1 third of M4. Next row is 0, 0, 0, 1, 0 followed by negative 1 over 27 M4 plus 1 over 18 M3 minus 1 over 6 M1 plus 1 over 3 M2. Now, observe these two matrices. In the first matrix, in the first 4 columns, there's a leading one. In the 5th column, there's no leading one here. That means this is a free variable. In the 5th column, there's no leading one. That means K4 is a free variable. If K4 is a free variable, means there are infinitely many solutions. That means there are infinitely many solutions for first vector equation. If there are infinitely many solutions, that means there exist non-zero solutions. That means there exist non-zero solutions for K1, K2, K3, K4, K5. If there exist non-zero solutions for K1, K2, K3, K4, and K5, that means the vectors A, B, C, D, E, they are linearly dependent, which means S is linearly dependent. So S is linearly dependent. For the second matrix, since on each column, since on each row there's a leading one. That means it's consistent. Since on each row there's a leading one, that means the second matrix is consistent. Since there is a leading one on each row, Then the vector equations k1a plus k2b plus k3c plus k4d plus k5e equal to m is always consistent. Then we know that S spans M22. But S is linearly dependent, so S is not a basis of M22. Since S is linearly dependent, S is not a basis of M22. Since S is linearly dependent, even though it spans M22, but S is linearly dependent, so it's not a basis. Even though it spans M22, but S is not a basis. S is not a basis of M22. Next example, find a basis of the solution space of the following homogeneous linear system. We know that the solution space of a homogeneous linear system is always a subspace of Rn, where n is an integer. And also we know that every vector space has a basis. So here let's find a basis for this solution space. So first of all, we will write the homogeneous linear system as an augmented matrix. So the first row is 1, 2, 0, 0, 4, 0. Second row is 2, -1, 2, 1, 1, 0. The third row is 0, 1, -1, -2, 2, 0. We try to reduce the matrix using Gauss-Jordan elimination. In the first row, that's the leading one. We try to make all entries below leading one to be 0. So I can first of all multiply first row by -2, add it to the second row. I get 1, 2, 0, 0, 4, 0 in the first row. Second row is 0, -2 times 2 is -4, -4 plus 1 is -5. 2, 1, that's -8. -8 plus 1 is -7. 0 stays the same. Third row stays the same. I get 1, 0, -1, -2, 2, 0. Next, in the second row, I try to make the first non-zero entry to be a leading one here. So I can switch row 2 and row 3. If I switch row 2 and row 3, first row is 1, 2, 0, 0, 4, 0. Second row is 0, 1, -1, -2, 2, 0. Third row is 0, -5, 2, 1, -7, 0. Next, we have leading one and second row. We try to make all entries above and below leading one to be 0. So I can multiply second row by -2, add it to the first row. I get 1, 0, 2, 4, 0, and 0. Leave second row the same. I get 0, 1, -1, -2, 2, 0. Next, I can multiply second row by 5, add it to the third row. Multiply second row by 5, add it to the third row. I get 0, 0, -3, -9, positive 3, and 0. Next, in the third row, we try to make the first non-zero entry to be a leading one. So I can divide the third row by negative 3. Divide the third row by negative 3. So first row stays the same. I get 1, 0, 2, 4, 0, 0. Second row is 0, 1, negative 1, negative 2, 0, 0. Third row is 0, 0, 1, 3, negative 1, 0. That's a 2 here. That's a leading one in the third row. Next, we try to make all entries above leading one to be 0. So I can first of all multiply third row by negative 2, add it to the first row. I get 1, 0, 0, negative 2, and positive 2, 0. Next, I can directly add the third row to the second row. I get 0, 1, 0, 1, 1, 0. So let's reduce the lower echelon form of an augmented matrix. Here you can see that in these two columns, there are no leading ones. That means x4 and s5, they are free variables. Next, rewrite the matrix back to equations. We have s1 minus 2s4 plus 2s5 equal to 0. s2 plus s4 plus s5 equal to 0. And x3 plus 3s4 minus s5 equal to 0. Next, move the free variables to the right side. I have s1 equal to 2s4 minus 2s5. s2 equal to negative s4 minus s5. x3 equal to negative 3s4 plus s5. Here, since s4 and s5 they are free variables, we choose two letters for s4 and s5. And s4 equal to t, and s5 equal to s. Choose any two variables for s4 and s5, since they are free variables. Next, we run the solution here. The solution is s1 equal to 2t minus 2s. s2 equal to negative t minus s. x3 equal to negative 3t plus s. s4 equal to t and s4 equal to s, where t and s can be any real numbers. That's the solution space. Next, we try to find a basis for the solution space. So in order to find a basis, I first of all write s1, s2, x3, x4, s5 as a column vector. Then here, s1 is 2t minus 2s. s2 is negative t minus s. x3 is negative 3t plus s. s4 is t, s5 is s. Here you can see that we have two variables. S and t. So separate s and t. Write t one column and write s in a different column. I have 2t minus t minus 3t t. If there's no t here, I write 0. Plus negative 2s, negative s, s. If there's no s here, write 0, and s. Then pull out t and s. If I pull out t, I get 2, negative 1, 3, 1, 0. If I pull out s, I get negative 2, negative 1, 1, 0, 1. Since all solutions is a linear combination of these two vectors, that's the basis of the solution space. Since all solutions commutated as a linear combination of these two vectors, that's the basis of the solution space. So the basis of the solution space is these two vectors. First vector, 2, negative 1, 3, 1, 0. Second vector, negative 2, negative 1, 1, 0, 1. Those are bases of the solution space. We can check they are linearly independent and they span the solution space. Next example, let W equal to SYZW in R4, such that x plus 2y is z, and y equal to W minus z. Let W be a subspace of R4. Find a basis of W. We know that every vector space has a basis. Here, let's find a basis for W. First of all, in W, all vectors satisfy that x plus 2y equal to z, and y equal to W minus z. Let me first of all rewrite these two equations. X plus 2y equal to z. It can be rewritten as x plus 2y minus z equal to 0. And y equal to W minus z can be rewritten as y plus z minus W equal to 0. Then we can rewrite this equation as a matrices. First row is 1, 2, negative 1, 0, 0. Second row is 0, 1, 1, negative 1, 0. Then we can reduce the matrices. Use Gauss-Jordan elimination. In the first row, that's a leading one, and the entry below leading one is 0. In the second row, that's a leading one. We try to make the entry above leading one to be 0. So I can multiply second row by negative 2, add it to the first row. I get 1, 0, negative 3, 2, 0, 0, 1, 1, negative 1, 0. That's the reduced rational form of this augmented matrix. Next, let's write this back to equation. I have x minus 3z plus 2w equal to 0. Second row is y plus z minus w equal to 0. Next, I can get s and y by itself. I get s equal to 3z minus 2w. Y equal to negative z plus w. Here, z and w, they are free variables. In these two columns, there's no leading one. Z and w, they are free variables. So I can simply let z equal to t, let w equal to s, then syzw can be expressed as x is 3 times t minus 2 times s. Y is negative t plus s. Z by itself is t. W by itself is s. Here you can see that there are two variables. I can separate s and t right in two columns. I have 3t negative t, t0 plus negative 2s, s0, s. Then I can pull out t, pull out s. If I pull out t, I get 3 negative 1, 1, 0 plus s times negative 2, 1, 0, 1. So you can see that for all vectors in W, it can be written as a linear combination of these two vectors, and they are independent, and they are linearly independent. So that's the basis of W. Since all vectors can be written as a linear combination of these two vectors, and they are independent, they are linearly independent. So that's the basis of W. You can check by yourself. They are linearly independent. And here we can see that all vectors in W can be written as a linear combination of these two vectors. That means these two vectors spans W. So that's the basis of W. Three, negative 1, 1, 0. Negative 2, 1, 0, 1. Next, for vector space, keep one idea in mind. In general, a vector space has more than one basis. For example, in examples 1 and 2, we can see that these two sets S, they are completely different sets, but they are both bases of R2. They are both bases of R2. So in general, a vector space has more than one basis. Next, let me show you the standard base of some vector space. The standard base of Rn is the set of E1 has 1 in the first entry, 0 in the rest. E2 has 1 in the second component, 0 elsewhere. And the last one, En, has 1 in the last entry, 0 elsewhere. That's the standard base of Rn. Next, let me show you the standard base of Pn. Pn is a set of polynomials with degree less or equal to n. Its standard base is 1, x, s squared, s cubed, go all the way up to Sn. That's the standard base of Pn. Next, let me show the standard base of matrices. Standard base of MMN. These spaces may be too big, so let me make it a little simpler. Let me find the standard base for M32. M32 is a set of all matrices with 3 rows and 2 columns. So the basis looks like this. 1 in the first entry, 0 elsewhere. Second element has 1 in the second entry, 0 elsewhere. Next matrix has 1 in the third entry, 0 elsewhere. Next one has 1 in the fourth entry, 0 elsewhere. Next element has 1 in the fifth entry, 0 elsewhere. Next one has 1 in the last entry, 0 elsewhere. That's the standard base of M32. Note, the standard base of Mn is defined similarly as M32. It's too big, I cannot write it out. Next, let me show you a theorem called uniqueness of basis representation. Let V be a finite-dimensional vector space, and let S equal to V1, V2, Vn be a basis in V. Then, for every vector V in V, V can be written as a linear combination of V1, V2, Vn in exactly one way. That's called uniqueness of basis representation. Next, let's prove it. Let V be a vector in V. We try to prove that V can be written as a linear combination of V1, V2, Vn in exactly one way. So in order to prove it, I first of all assume V can be written as a linear combination of V1, V2, Vn in two ways. Then try to show that that's impossible. So assume V can be written as a linear combination of V1, V2, Vn in two ways. We try to show that that's impossible. Then V equal to K1 V1 plus K2 V2 plus Kn Vn, and V equal to L1 V1 plus L2 V2 plus Ln Vn. For some scalars, K1, K2, Kn, and L1, L2, Ln. So assume V can be written as a linear combination of V1, V2, Vn in two ways. We try to prove that that's impossible. Then for these two equations, if I subtract these two equations, what do we get? If I subtract these two equations, V minus V equal to 0. If I subtract these two terms, I have K1 minus L1 times V1. If I subtract these two terms, I have K2 minus L2 times V2. If I subtract the last term, I have Kn minus Ln times Vn. So if I subtract these two equations, on the left side, V minus V is 0. K1V minus L1V, I can factor V1 out. I get K1 minus L1. For K2V2, L2V2, when I subtract, I can factor V2 out. I have K2 minus V2. Then, for the last term, when I subtract KNV minus LNV, I can factor out Vn. What's left is Kn minus Ln. Now, since V1, V2, Vn is a basis of V, then V1, V2, Vn, they are linearly independent. Now, let's look at this vector equation here. Since the right side of the vector equation is a linear combination of V1, V2, Vn, and equal to 0, and also, since V1, V2, Vn, they are linearly independent, then the only solution to this vector equation is K1 minus L1 equals 0, K2 minus L2 equals 0, and Kn equals Ln equals 0. So, the only solution to the above equation, to the above vector equation, are K1 minus L1 equals 0, K2 minus L2 equals 0, and Kn minus Ln equals 0. We treat this as scalars of V1, V2, Vn. So all scalars must be 0 in this vector equation. Therefore, K1 equal to L1, K2 equal to L2, and Kn equal to Ln. If K1 equal to L1, K2 equal to L2, Kn equal to Ln, that means these two representations are exactly the same. If K1 equal to L1, K2 equal to L2, Kn equal to Ln, that means two representations are exactly the same. So V has exactly one representation. So V can be written as a linear combination of V1, V2, Vn in exactly one way. Since these two representations are exactly the same. So V can be written as a linear combination of V1, V2, Vn in exactly one way. That complete the proof. So keep in mind that if S is a basis in V, then for every vector in V, this vector can be written as a linear combination of V1, V2, Vn in exactly one way. That's called uniqueness of basis representation. Next theorem. Let V be a finite dimensional vector space, and let S equal to V1, V2, Vn be a basis in V. Here S has n vectors. If T is a subset of V with more than n vectors, then T must be linearly dependent. So this theorem says, if a basis in V has only n vectors, then for any subset of V with more than n vectors, it must be linearly dependent. Let's prove it. Here, T is a subset of V, so let T equal to U1, U2, up to Um. Where M is more than N. Assume T has more elements than S. Since S equal to V1, V2, Vn is a basis, is a basis in V. Then S spans V. S spans V means every vector in V can be written as a linear combination of V1, V2, Vn. So U1 can be written as a linear combination of V1, V2, Vn. So assume U1 can be written as A11 times V1 plus A21 times V2 plus AN1 times Vn. Since T is a subset of V, so every element here, U1, U2, Un, belongs to V. Since S spans V, every vector in V can be written as a linear combination of V1, V2, Vn. Similarly, U2 can be written as A12 V1 plus A22 V2 plus AN2 Vn. Similarly, UM can be written as A1M V1 plus A2M V2 plus ANM Vn. Next, we shall show that T must be linearly dependent. So I set K1 U1 plus K2 U2 plus Km Um equal to 0. If this vector equation has a non-zero solutions for K1, K2, or Km, then T must be linearly dependent. If this vector equation has a non-zero solutions for K1, K2, or Km, then T must be linearly dependent. Now, let's compute K1, U1, K2, U2, and Km, Um. What's K1, U1? In order to compute K1, U1, in the first equation here, I multiply both sides by K1. So in the first equation, I multiply both sides by K1. I get K1 U1 equal to K1. I distribute K1 to each of them. I get K1 A11 V1 plus K1 A21 V2 plus K1 AN1 Vn. Next, in the second row, I multiply both sides by K2. In the second equation, I multiply both sides by K2. I get K2 U2 equal to K2 A12 V1 plus K2 A22 V2 plus K2 AN2 Vn. Then continue. In the last row, I multiply both sides by Km. So I get Km Vm equal to Km times A1M V1 plus Km times A2M V2 plus Km times ANM times Vn. Now, if I add the left side together, if I add both sides together, on the left side, I have K1 V1, K2 V2 plus Km Vm. We know that K1 U1, K2 U2, Km Um together is 0. So if I add both sides, the left side becomes 0. If I add both sides together, left side becomes 0. On the right side, Sorry, this is um. On the right side, I have add everything together. I have, let me add each column individually. For the first column, I have K1 A11 plus K2 A12 plus Km A1M times V1. If I add the first column together, that's what I get here. K1 A11 plus K2 A12 plus Km A1M. Then factor V1 out. Since in the first column, V1 is a common factor. So add them together, factor V1 out. Then for the second column, do the same thing. Add them together, V2 is a common factor, I can pull out V2. So I get K1 times A21 plus K2 times A22 plus Km times A2M. Then factor V2 out. Continue in the last column. In the last column, add them together, Vn is a common factor, so I can factor Vn out. I get K1 times An1 plus K2 times An2 plus Km times Anm. Then factor Vn out. I have Vn outside. So 0 equal to this. This is a linear combination of V1, V2, Vn. Here, this is a linear combination of V1, V2, Vn. If this vector equation equals 0, that means all coefficients of V1, V2, Vn must be 0. Since S equal to V1, V2, Vn is a basis. It's a basis of V. Then V1, V2, Vn, they are linearly independent. Since V1, V2, Vn, they are linearly independent, and this combination equals 0, that means all scalars must be 0. That means the only solution here is 0, which means all scalars must be 0. So this scalar is 0. This is a scalar of V1. This is a scalar of V2. All scalars must be 0, since they are linearly independent. All scalar here must be 0. So K1 A11 plus K2 A12 plus Km A1M equal to 0. And K1 A21 plus K2 A22 plus Km A2M must be 0. And similarly, in the last row, K1 AN1 plus K2 AN2 plus Km ANM equal to 0. Here, the case K1, K2, Km, they are unknowns. Here we have M unknowns. K1, K2, Km, they are unknowns. In this vector equation, K1, K2, Km, they are unknowns. So here, in this system of equations, we have M unknowns, and there are N equations. A12, A2, A11, A21, AN1, there are N equations. there are m unknowns, n equations. So in the above homogeneous linear system of equations, there are m unknowns from k1, k2 until km. There are m unknowns. And there are n equations from a11, a21 until an1. There are n equations. Since m is greater than n, then there are more unknowns than number of equations. Since m is greater than n, there exists more unknowns than number of equations. There are more unknowns than number of equations. And in chapter 1, we know that for any homogeneous linear system of equations, if there are more unknowns than number of equations, there exists infinitely many solutions. Since the trivial solution is one of the solutions, there must exist non-trivial solutions. Therefore, the homogeneous linear system of equations has non-trivial solutions. Since the homogeneous system have infinitely many solutions, and the trivial solution is one of the solutions, there must exist non-trivial solutions. Non-trivial solutions means at least one of the k1, k2, km is not zero. They are not all zeros. Non-trivial solutions means k1, k2, km, they are not all zeros. Hence, there exist solutions for k1, k2, km such that not all of them are zeros. And in a vector equation here, in a vector equation, k1 u1 plus k2 u2 plus km uvm equal to 0. If there is non-zero solutions for k1, k2, or km, that means the vectors u1, u2, um, they are linearly dependent. Therefore, the set T with u1, u2, um must be linearly dependent. Hence, T with vectors u1, u2, um is linearly dependent. Let's complete the proof for this theorem. T must be linearly dependent. So keep in mind, this theorem says, in a vector space, if there's a set which contains more elements than a basis, then the set must be linearly dependent. If a set has more elements than a basis, then the set must be linearly dependent. Next theorem. Let V be a finite-dimensional vector space, and let S equal to V1, V2, Vm be a basis in V. Here S has n vectors. From V1, V2 to Vn, there are n vectors. If T is a subset of V with fewer than n vectors, then T does not span V. So this theorem says, if a subset of V has fewer vectors than a basis, then the subset does not span V. Now let's prove it. First of all, let T be the set of U1, U2, up to Um. So T has m vectors. Since T has fewer than n vectors, then m must be less than n. So T equal to U1, U2, Um with m less than n. Now, in order to prove this theorem, let me first of all prove that T has a linearly independent subset. T has a linearly independent subset T prime, such that span of T prime equal to span of T. So first of all, let me claim T has a linearly independent subset T prime. Such that span of T prime equal to span of T. So, in order to prove this theorem, let me prove this claim first. So, for the claim, let's consider two cases. T by itself, it could be either linearly dependent or linearly independent. So, in case 1, let's first of all consider T is linearly independent. If T is linearly independent, T by itself, T is a subset of itself. T is a subset of itself. So I can let T prime equal to T. Then T prime is a subset of T, because T is a subset of itself. Let T prime equal to T. Then T prime is a subset of T, because T is a subset of itself. And T prime is linearly independent. Because T is linearly independent. And span of T prime equal to span of T. Since T prime equal to T, span of T prime equal to span of T. That's case 1. When T is linearly independent, T has a linearly independent subset, which is such that span of T prime equal to span of T. That's case 1. Case 2, T is linearly dependent. Then some vectors in T can be written as a linear combinations of the others. Then, by plus or minus theorem, if a vector commuted as a linear combination of the other vectors in a set, if I remove the vector, the span of the set stays the same. Then, by plus or minus theorem, if we keep removing these vectors from T, finitely many times, we can remove this vector from T at most m times. Since T has m vectors, we can remove this vector from T at most m times. If we keep removing this vector from T finitely many times, we can eventually obtain a linear independent subset of T. Let's call this set T prime, such that span of T prime equal to span of T. By plus minus theorem, if I remove these vectors that commuted as a linear combination of the other vectors, the span stays the same. The span of the set stays the same. Of course, we must remove this vector one by one. We must remove one vector at a time. By doing the process finitely many times, we can obtain a subset T prime, which is such that T prime is linearly independent and span of T prime equal to span of T. That complete the proof. That T always has a linearly independent subset T prime, such that span of T prime equal to span of T. So that's the claim. That's the claim and proof. T always has a linearly independent subset T prime, such that span of T prime equal to span of T. Next, we try to prove T does not span V. We try to prove it by contradiction. So assume T spans V. Prove by contradiction. Assume T spans V. Then span of T equal to V. If T spans V, then span of T equal to V. Since T has a linearly independent subset T prime, since T has a linearly independent subset T prime with span of T prime equal to span of T, that's our claim here. T always has a linear independent subset T prime, such that span of T prime equal to span of T. Since T has a linear independent subset T prime with span of T prime equal to span of T, then span of T prime equal to V, because span of T is V, so span of T prime is also V. Since T prime is linearly independent, and T prime spans V, then T prime is a basis of V. Since T prime is linearly independent and T prime spans V, then T prime is a basis of V. Since T has fewer vectors than S, since T has fewer vectors than S, so you can see that T has fewer vectors than S. And T prime is a subset of T. That means T prime also has fewer vectors than S. Or in other words, we can say S has more vectors than T prime. Or in other words, we can say S has more vectors than T prime. Since T prime is a basis of V, since T prime is a basis in V, and S has more vectors than T prime, then by the previous theorem, if a set has more vectors than a basis, the set must be linearly dependent. By the previous theorem, if a set has more vectors than a basis, the set must be linearly dependent. Since T prime is a basis, and S has more vectors than T prime, then by the previous theorem, S must be linearly dependent. But S is a basis here. S is a basis in V. It must be linearly independent. So that's a contradiction. S is a basis. It cannot be linearly dependent. That's a contradiction. If we find contradiction, that means our assumption must be wrong. That means T doesn't span V. If we find contradiction, that means our assumption must be wrong. That means T does not span V. Hence T does not span V. That complete the proof for the theorem. So keep in mind that if a set has fewer vectors than a basis, the set does not span V. If a set has fewer vectors than a basis, then the set does not span V. Next, based on the previous two theorems, let me show you another theorem. Let V be a finite-dimensional vector space. Then all bases in V contain the same number of vectors. Let's prove it. In order to prove all bases in V contain the same number of vectors, we try to prove that any two bases in V contain the same number of vectors. We try to prove that any two bases in V contain the same number of vectors. So I first suppose that S and T be two bases in V. We try to prove that S and T have the same number of vectors. We try to prove that S and T have the same number of vectors. If S has more vectors than T, then since T is a basis, then by the previous theorem we know that a set has more elements, a set has more vectors than a basis, must be linearly dependent. A set has more vectors than a basis, must be linearly dependent. Since S has more vectors than T, and T is a basis, S must be linearly dependent. That's a contradiction, that's impossible. So S cannot have more vectors than T. So S cannot have more vectors than T. But what if S has fewer vectors than T? What if S has fewer vectors than T? Then, by the previous theorem, since T is a basis, we know that a set with fewer vectors than a basis doesn't span V. A set with fewer vectors than a basis does not span V. Then S does not span V. Since S has fewer vectors than T, and T is a basis, a set with fewer vectors than a basis does not span V. A set with fewer vectors than a basis does not span V. That's also impossible. Since S is a basis, that's also impossible. So S cannot have fewer vectors than T. Since S cannot have more vectors than T, and S cannot have fewer vectors than T, then S must have exactly the same number of vectors as T. Therefore, S must have the same number of vectors as T. So let's complete the proof. All bases in V must have the same number of vectors. In a vector space, all bases must have the same number of vectors. Next, based on the previous theorem, let me introduce the dimension of a vector space. Let V be a finite dimensional vector space. The dimension of V is defined to be the number of vectors in one of its bases. According to the previous theorem, we know that all bases in V have the same number of vectors. So we define dimension of V to be the number of vectors in one of its bases. And the dimension of V is denoted by DIM, dimension of V. That's how we define the dimension of a vector space. Next, let me show you a special case. The zero vector space. The zero vector space is the vector space that contains only the zero vector. And we know that the zero vector space is spanned by empty set. The zero vector space is spanned by an empty set. So the empty set is the only basis of the zero vector space. The empty set is the only basis of the zero vector space. Since the empty set has no vectors, so we define the dimension of the zero vector space to be 0. Since that's the empty set only basis of the zero vector space, and the empty set contains no vectors, so the dimension of the zero vector space is 0. That's a special case. The dimension of the zero vector space is 0. That's a special case. Next, let me show you the dimension of some familiar vector space. For dimension of Rn, that's n. Because the standard basis of Rn is E1, E2, En. There are m vectors in the standard base of Rn. So the dimension of Rn is n. And the dimension of Pn is n plus 1. Because the standard basis of Pn is 1, x squared, x cubed, up to x to the power n. For number 1, we can consider that's x to the power of 0. X, we can consider that's x to the power of 1. So consider s will not increase from 0, 1, 2 to n. From 0 to n, there are m plus 1 vectors. From x0 to Sn, there are m plus 1 vectors. If there are m plus 1 vectors in the standard base of Pn, the dimension of Pn is m plus 1. And the dimension of Mn, the set of all m by n matrices, is m times n. For example, for M32, for the set of all 3 by 2 matrices, there are 6 vectors. There are 6 vectors in the standard basis. So similarly, for the set of all m by n matrices, it will be m times n vectors. It will be m times n vectors in the standard basis. Therefore, the dimension of Mmn is m times n. Mmn is the set of all m by n matrices. Its dimension is m times n. Note, if a vector space is infinite dimensional, for example, R infinity, the set of all infinite sequence, P infinity, the set of all polynomials, F from negative infinity to infinity, the set of all functions, defined from negative infinity to infinity. They are infinite dimensional vector space because they cannot be spanned by a finite set. This vector space cannot be spanned by a finite set. They are infinite dimensional vector spaces. Then its dimension is denoted by infinity. If a vector space is infinite dimensional, its dimension is denoted by infinity. So dimension of R infinity is infinity. Dimension of P infinity is infinity. Dimension of F from negative infinity to infinity is infinity. And in an earlier example, note, in example 5, we are looking for a basis of the solution space. And here we see that the basis of the solution space has 2 vectors. That's the basis of the solution space. There are 2 vectors. Since there are two vectors in a basis, that means the dimension of the solution space is 2. If there are two vectors in a basis of the solution space, that means the dimension of the solution space is 2. Example 5. The dimension of the solution space is 2 because there are two vectors in a basis of the solution space. Example 2 here, you can see that there are two vectors in a basis of the solution space. And similarly, in example 6, W is a subspace of R4, and we are looking for a basis of W. Here, that's the basis of W. That's the basis of W. We can see that there are two vectors in a basis of W. There are two vectors in the basis of W, which means the dimension of W is also 2. Since there are two vectors in the basis of W, dimension of W is 2. In example 6, the dimension of W is 2. Because there are two vectors in a basis of W. Next, let me show you a theorem. Let V be a vector space with dimension of V equal to n. Part A. If a subset of V has more than n vectors, then it must be linearly dependent. Part B. If a subset of V has fewer than n vectors, then it does not span V. This theorem is equivalent to earlier theorems. The proof is very simple. Let me show you here. Since dimension of V is n, that means every basis in V has n vectors. Every basis in V has n vectors. Let T be a subset of V. Part A. If T has more than n vectors, then, according to the earlier theorem, we know that a subset of V with more vectors than a basis must be linearly dependent. A subset of V with more vectors than a basis must be linearly dependent. Then T must be linearly dependent. Then T must be linearly dependent. Since it has more vectors than a basis. Let's complete the proof for part A. For part B, if T has fewer than n vectors, Then, according to the earlier theorem, we know that a subset of V with fewer vectors than a basis does not span V. A subset of V with fewer vectors than a basis does not span V. Then we know that T cannot span V. Since T has fewer vectors than a basis. That complete the proof for part B. So keep this here in mind. If V has dimension n, any subset with more than n vectors are linearly dependent, and any subset with fewer than n vectors does not span V. Next, based on this theorem, let's reconsider some earlier examples. Example 3 and example 4. Let's redo example 3. In example 3, we have a set S. S contains two vectors, and we try to determine whether S is a basis in P2. With this new theorem here, we can answer the question in a much simpler way, without doing this long computation. So, we try to determine whether S is a basis in P2. We know that dimension of P2 is 3, because dimension of Pn is always n plus 1. So dimension of P2 is 3. And S has only two vectors. S has only two vectors. Then, according to this theorem here, if a subset of V has fewer than n vectors, it does not span V. Since 2 is less than 3, we know that S does not span P2. Hence, S is not a basis of P2. Next, let's redo example 4 using new theorem. In example 4, S is a set of 5 matrices, and we try to determine whether S is a basis of M22. Let's answer this question using the new theorem. It will be much simpler. We don't need to do this long process. This long process is very hard. With the new theorem, we don't need to do the long computation here. We can answer the question in a much simpler way. Let's redo example 4. Since dimension of M22 is 4, because 2 times 2 is 4, dimension of MMN is always M times N. We multiply the dimension. So dimension of M22 is 2 times 2 is 4. And S has 5 vectors. Here S has 5 vectors. 1, 2, 3, 4, 5. According to the new theorem here, if a subset of V has more than n vectors, then it must be linearly dependent. Since phi is more than 4, then S is linearly dependent. Hence, S is not a basis in M22. A basis must be linearly independent. Hence, S is not a basis in M22. So, with this new theorem, we can answer example 3 and 4 in a much simpler way, without doing this long computation. So here you can see that this theorem is very useful. When dimension of V is n, if a subset has more than n vectors, then it must be linearly dependent. And if a subset has fewer than n vectors, then it doesn't span V. However, what if a subset has exactly n vectors? Then how can we determine whether the subset is linearly independent or whether it spans V? In general, it's not easy. But let me show you some special case. In general, it's not easy, but let me show you some special case. In a vector space V, let S be a subset of V, and the number of vectors in S is equal to the dimension of V. If V is Rn, let A be the matrix whose columns are the components of each vector in S. So, in the earlier example, if S is a subset of Rn, let A be the matrix whose columns are the components of each vector. Let A be the matrix whose columns are the components of each vector, v1, v2. If V equal to Pn, let A be the matrix whose columns are the coefficients of each polynomial in S. So if V is Pn, in example 3 here, if S is a subset of P2, let A be the matrix whose columns are the coefficients of its functions, of its polynomials. Let A be the matrix whose columns are its polynomials, are the coefficients of the polynomials in S. So, coefficient of 1 is 1, coefficient of x is 0, coefficient of s squared is 1, coefficient of 3 is 3, coefficient of x is 2, coefficient of s squared is 0. So let A be the coefficients of the polynomials in S. If V is m and n, then let A be the matrix whose columns are the entries of each matrix in S. So, if V is M22 and S is a subset of M22, let A be the matrix whose columns are the entries of each matrices in S. Whose columns are the entries of each matrices 2, 1, 0, 0, 1, 0, 3, 0, 0, 0, 2, 3, and so on. So let A be this matrix. Let A be the matrix whose columns are the entries on each matrices. In all above cases, A is a square matrix. In all above cases, A is a square matrix. For example, in R2, dimension of R2 is 2. If there are 2 vectors here, I put the entries of the 2 vectors in columns. I get a 2 by 2 matrix. A is a square matrix. In P2, dimension of P2 is 3. If we get 3 vectors, here we only have 2 vectors. But if we have 3 vectors, we will have 3 columns here. So A will be a 3 by 3 matrix. Here P2 has dimension 3. if there are 3 vectors in S, then if I put the components in columns, if I put the coefficient in columns, I'll have a 3 by 3 matrix. And in M22, dimension of M22 is 4. 2 times 2 is 4. If there are 4 matrices in S, when I put their components, when I put their entries in columns, I have 4 columns. That's a square matrix. 4 rows, 4 columns. That's a square. If there are 4 matrices here, and I put their entries in columns, it'll be 4 columns here. It'll be 4 columns here. That's a square matrix. So in all above cases, A is a square matrix. Then for square matrix, we can find the determinant of A. If determinant of A is not 0, then we know that then the vector equation kv1 plus kv2 only has trivial solution. This equation only has trivial solution, means k1 is 0, k2 is 0. So the vectors, they are linearly independent. And also, this vector equation k1 v1 k2 v2 equal to b is consistent. If it's consistent, we have solutions for k1 and k2. That means the vector v1 v2 spans R2. So in the case, if determinant of A is not 0, then S is linearly independent and S spans V. Hence, S is a basis in V. However, if determinant of A is 0, then there exists non-zero solutions for k1 or k2, which means the vectors v1, v2, they are linearly dependent. And also, this equation k1, v1, k2, v2 equal to b is not always consistent. If it's not always consistent, the vectors v1, v2 doesn't span R2. Therefore, if determinant of A is 0, S is linearly dependent, and S does not span V. Hence, S is not a basis in V. So, if the dimension of V equal to the number of vectors in S, in this 3 special case, we can form a square matrix of A. Then take determinant for A. If determinant of A is not 0, then S is a basis in V. If determinant of A is 0, then S is not a basis in V. So keep this rule in mind. This rule only works for these 3 special cases: Rn, Pn, and Mn. Next, based on this rule here, let's reconsider some earlier examples. Example 1 and example 2. Let's redo example 1. In example 1, S is a set of 2 vectors. We try to show that S is a basis in R2. So, for R2, we know that dimension of R2 is 2. And S has 2 vectors. That's in the case that the number of vectors in S is equal to dimension of V. In this case, in Rn, in R2 is a special case of Rn. In R2, let A be the matrix whose columns are components of each vector in S. So, let A be the matrix whose columns are the components of each vector in S. So component of the first vector is 2, 3. Component of the second vector is 5, 1. Then A here is a square matrix. The determinant of A. Determinant of A is 2 minus 15 equal to negative 13, which is not 0. If determinant of A is not 0, then S is linearly independent and S spans V. Hence, S is a basis in V. So, S is a basis in V. Here our V is R2. So S is a basis in R2. Next, let's redo example 2. Example 2. S has two vectors. Show that S is a basis in R2. Again, dimension of R2 is 2. And S has two vectors. That's the case that the number of vectors in S is equal to dimension of V. Number of vectors in S equal to dimension of R2. In this case, find matrix A. A is a matrix whose columns are the components in each vectors in S. A is a matrix whose columns are the components of each vector in S. So the first column is 1, 1, 4. Second column is 2, 1. Then take determinant of A. Here determinant of A is 1 minus A, which is -7. -7 is not 0. Then, by the rule here, if determinant of A is not 0, then S is linearly independent and S spans V. Hence, S is a basis in V. So, S is a basis in V. Here V is R2. So S is a basis in R2. The same thing works for polynomials or matrices. The same thing works for Pn and Mn, polynomials and matrices. Next, let me show you a theorem. Let V be a vector space with dimension of V equal to n, and let S equal to V1, V2, Vn be a subset of V. Here S has n vectors. From V1, V2 to Vn there are n vectors. Part A, if S is linearly independent, then S spans V. Part B, if S spans V, then S is linearly independent. Let's prove it. Let's prove part A first. Part A says S is linearly independent. We try to prove that S spans V. Here we try to prove by contradiction. Assume S does not span V. We try to show that that's impossible. So prove by contradiction. Assume S does not span V. If S does not span V, that means there exists a vector U in V. There exists a vector U in V such that U doesn't belong to span of V. U doesn't belong to span of S. Since S is linearly independent. Since S is linearly independent, and U doesn't belong to span of S, then by plus minus theorem, by the plus-minus theorem, the first part says, if S is linearly independent, and U cannot be written as a linear combination of vectors in S, that means U doesn't belong to span of S, then if I add U to S, it's still a linearly independent set. Then if I add U to S, it's still a linear independent set. Here, let S prime equal to S union U. Then S prime has m plus 1 elements. Since S has m vectors plus one more vector, S prime has m plus 1 vectors. S prime has m plus 1 vectors. And S prime is linearly independent. However, according to the previous theorem, we know that if a subset of V has more than m vectors, it must be linearly dependent. According to the previous theorem, we know that if a subset of V has more than m vector, it must be linearly dependent. But according to the previous theorem, since dimension of V is n, and S prime has m plus 1 vectors, it must be linearly dependent. So here we see that the plus-minus theorem contradicts the previous theorem. Here the plus-minus theorem contradicts the previous theorem. That means our assumption must be wrong. If we find contradiction, that means our assumption must be wrong. So S does spans V. So S does spans V. It's a contradiction. That means our assumption was wrong. That means S does span V. Based on this assumption here, the plus-minus theorem contradicts the previous theorem. That means something was wrong. That means our assumption was wrong. That means S does span V. It's a contradiction. So S spans V. S does span V. That's a proof for part A. For part B, if S spans V, we try to prove that S is linearly independent. So again, try to prove by contradiction. Assume S is linearly dependent. assume S is linearly dependent. Assume S is linearly dependent. Then there exists a vector U in S such that U can be written as a linear combination of other vectors in S. There's a U in S such that U can be written as a linear combination of other vectors in S. Then, by plus-minus theorem, if U can be written as a linear combination of other vectors in S, if I remove U from S, the span of S and S minus U is exactly the same. If I remove U from S, the span of the set stays the same. By the plus-minus theorem, span of S is the same as span of S minus U. Let S prime be span of S minus U. Then S prime has m minus 1 vectors. Since S spans V, then V equal to span of S, hence equal to span of S prime. So S prime also spans V. According to the previous theorem, if dimension of V is n, a subset with fewer than n vectors does not span V. A subset with fewer than n vectors does not span V. So here, according to the previous theorem, since dimension of V is n, and S prime has only n minus 1 vectors, then S prime cannot span V. S prime cannot span V. Let's contradict with the plus-minus theorem. Plus-minus theorem says S prime spans V, but the previous theorem says S prime cannot span V. Therefore, if we see a contradiction, that means our assumption was wrong. That means our assumption in the beginning was wrong. This assumption caused contradiction. That means it's wrong. That means it must be wrong. S must be linearly independent. It's a contradiction. That means our assumption was wrong. So S must be linearly independent. Let's complete the proof. Let's complete the proof. So this theorem says, if dimension of V is n, and S has n vectors, then S is linearly independent if and only if S spans V. S is linearly independent if and only if S spans V.